So since it's my last talk, I would like to thank the organizer for the wonderful job and for all the work they asked the lecturers to do.
You're welcome.
I think I never worked so much, that much, but okay. I mean, I will be able to take vacations in Paris. Okay. So now the problem is that we clearly we have to deal with quantifiers, and we want to associate formulas with quantifiers, geometric objects. Okay, this is not very clear. We want something else. We want these objects related to counting points. Okay. So here there will be a little first order logic. So to have a nice way to express things, I will now consider, so we were considering the Grothendieck ring of varieties, but as I mentioned, one can also consider Grothendieck ring of first order theories. So this is what I will explain now. So I take L language, first order language. T theory. And we consider the Grothendieck ring of T. So I take the abelian group on, so I will consider formulas, first order formulas. So modulo certain relations. So the first relation, I was considering isomorphism classes. So here I have not still not constrained by isomorphism classes. So I should explain what I mean by isomorphic formulas. So it should mean that they define the same definable sets, or that these definable sets are isomorphic by a bijection whose graph is definable. So should I explain it at on the blackboard, or are you okay with these words?
Write it.
Okay. So to write it, it becomes complicated. So assume phi is a formula in L with free. Sorry?
They want you to write a little bit louder.
Okay? Here. So I take phi formula in L with three variables x, y prime. So different free variables. no reason that they have the same number of variables. Okay. So you set phi is isomorphic to phi prime if there exists psi in L with three variables x on x prime, such that, so, I mean, I'm happy if you understand better if I write this, because for me it's just impossible to understand what I will write, but okay. Okay, but no problem. So it's logic, so we should count the number of parentheses. Okay, this is just a formal way to tell, you know, in a much more clear way what I told before.
On second thoughts, maybe you should just say it.
Oh no, the second one I will write it. So the second one was inclusion of a closed subset. So here it's very easy to state. It's just that if you take the reunion of two formulas, it's the same as what? As here. Yes?
The first square bracket
Is missing?
the first square bracket in the first line has nothing to do with the square bracket below.
There's a problem. Okay, so this shows. I mean that I'm not a professional logician. I'm sorry. I'm sorry for. I hope I do not offend anybody here. Okay, so okay, and one puts. So this is it, and so puts there is a ring structure. It is what you guess. So I put x to so x and x prime are different sets of free variables. And so, in fact, we are concerned only with counting points. Okay, so I should say it otherwise. I mean, we want to construct geometric objects associated to formulas, and we want that when we pass to counting points in finite fields, we obtain the number of points defined by your formula, satisfying your formula. So, yes?
In two, the people have the same variables. In two, they have the same.
Yes, here they are the same. Yes, yes. Otherwise, it becomes these two relations becomes in contradiction. Okay, so. Okay, so this morning you had a nice introduction on pseudo-finite fields, and so we will consider pseudo-finite fields. So the theory I will consider will be pseudo-finite fields. So And we consider the corresponding, so the language is the language of rings. So we want to attach invariance, geometric. So the best oh yes, there is a base field. Okay, I will consider formulas with coefficients in a given field. So so L is language of rings, and I also have symbols for elements in K. So with parameters in small k. Okay. Yes, yes. Yes, yes.
What was the question?
The question is this. It's pseudo-finite fields containing K.
So the theory here is a theory of pseudo-finite fields.
Containing K.
Diagram.
Yes, absolutely.
Multiplication table of K.
Absolutely.
Yeah?
Yes. Yes. And K will be of characteristic 0. Okay. So don't copy this in your notes because I don't know how to construct such a morphism. Okay. First, if one thinks a little, I think it's natural to transfer this by Q. But even that, I don't know how to construct. So, and I should explain what it means. So it's hard to reconstruct a variety by just knowing its number of points modulo or variety of a Q by knowing its number of points finite field. For instance, isogenous elliptic curves will have the same number of points. So a priori, there is no way of choosing a specific variety. But two isogenous elliptic curves, they define the same Chow motif. So that's one of the reasons why maybe it's not stupid to look to Chow motif. So we shall consider Chow motifs. Since isogenous elliptic curves have same Chow motif. Another reason to consider Chow motif is that we will use some work on some other people. So to relate the formulas with geometry, the problem is that you have quantifiers, so you should eliminate the quantifier. So I not use a non-quantifier elimination for pseudo-finite fields. Okay. So you have several quantifier eliminations. I mean, often you have several different quantifier elimination theorems because you extend the language usually, so you have several possible ways of extending the language. Okay? So there is an old approach due to Kiefer, a student of Axe, and I mean our work is quite close to that of Axe. And so in some sense, it gives you virtual varieties with coefficient in Q, that gives you the correct number of points. But the problem is that you have many different ways to construct, to do such an elimination of quantifiers. And a priori, they will give you different objects here. So the whole point is to be able to construct a canonical object. Okay? So the approach that is, seems to be well suited for that problem is approach with Galois stratification. So I will not explain in very precise in terms what Galois stratification. I think that Wednesday morning, I mean, in the student lectures, in the project, you will see more about Galois stratification and quantifier elimination with Galois stratification. I just explained the basic objects so I think they first appear in a work by Fried and Sacerdote, and in some and also some other papers by Fried and some other people. But the whole theory is explained in detail in Fried and Yarden's book. Which you sell for $5. I am right? Okay. So, oh, I should not say it publicly. I'm sorry. So the basic objects. So you have some A, say the variety of some affine space, say smooth if you want, and you have some C over a Galois cover. This means in geometrical terms that the morphism is finite and ramified, and that you have a group acting on it, which transitive on the fibers, and which that identifies C, A with the quotient of C by the group. So what does that mean to be in the image in such a? So this is a very special case of morphism, which will give you a quantifier you want to eliminate. Okay. So what does it? What does it mean for a rational point here to be in the image of the rational point here? Okay. So in terms of decomposition groups, it means that the decomposition group is trivial. Okay. So let's call this F. So take X, a rational point over some field capital K. So there exists Y in C of capital K with F of Y is X, if and only if the decomposition group above X is trivial. So now the whole idea of the approach by Fried is to consider not only the trivial decomposition group, but any decomposition group. So decomposition group does not exist really as a group, I mean, because it's only defined up to conjugacy. So you consider the Galois cover plus a family of subgroups of G stable by conjugation. It's not the subgroups that are supposed to be stable, but the family of subgroups. Okay. So that's the basic data. And to such a data, you consider the set of points in A. So family, call it C, with decomposition group in C. And so Fried and Yarden, or Fried and Co. Theorem, elimination of quantifier, states that for as far as pseudo-finite fields are concerned, you can replace ring formulas with quantifiers by such a kind of formula. They are not really formulas. I mean, strictly speaking, they are not really first-order formulas, but they are more geometric objects. But they define subsets of the affine space. And in this way, you can eliminate the quantifiers. And the number of points, so for so I'm thinking of a number of points, but there is no number of points because we are considering pseudo-finite fields. So what do I mean by number of points? I mean the following. I mean, assume now small k number field. Then by it's more or less ACT theorem, it amounts to the same to looking to all pseudo-finite fields containing k, or to look at all finite residue field of k. So we will do this, we will apply this over k, and we will count. So I should give a name to this. So I should give a name. I call H, say of so this is the data, and I take so notation are not they're not so Kp, this is the residue field. Why not? So just the number, this set of points. Kp to the power m with a decomposition group in C. So you can count it. So, and it's easy to count with this data. Maybe I will not write the formula, but it's expressed in terms of a central function on G. So now all the geometric data we are concerned with are just Galois cover and some central function on G built out of C. And so this is very geometric, and this is where the motifs come. So Chor motifs. So Chow motifs are a way, may be viewed as a way to linearize algebraic varieties. For instance, assume G is an abelian group, not an abelian group, a finite group, acting on X, say smooth projective. If X was a linear object, you would get something like this. You would get decomposition of other characters. Of course, it doesn't mean anything in the category of varieties. Okay? But it's well known that, for instance, when you count points, you see such a phenomenon. For instance, you have the classical case of Fermat varieties, where you have a huge group acting on it, and the number of points can be you can express it into packets. Each packet comes from a place where you have certain action by certain characters, and this gives you Jacobi sums. So the idea of motifs is that one of the usefulness is that they may give meaning to that. So in fact, you have so in Chow motifs. So what are Chow motifs? So take still X smooth projective. So you take gamma correspondence. What does that mean? So you take the Cartesian product, and you take a cycle. But a cycle is just a linear combination of subvarieties. You assume everybody is of dimension n, dimension of X. So a typical example is a graph of a morphism. Okay. So now one would like to compose correspondences. And to compose them, one need to caution by an equivalence relation. To replace, so this is n-dimensional cycles. Or maybe I should write show. What is it? In fact, I work with coefficient in Q. But the point is that you can't caution by some equivalence relation, which is a rational equivalence. So if I am in some variety y, and if I have z and z prime in some cycles of codimension, so D is codimension. Here it was the same because it's we are in the middle dimension, so codimension is dimension. then they are linearly equivalent. Or more, if there exists W of of dimension 1 more, F meromorphic on W, such that Z minus Z prime is a divisor of F. So this means that one is the zero locus and the other one is the infinity locus. So then you write Z equivalent to Z prime. It's not yet an equivalence relation, so you take the equivalence relation generated by this. And now this is the Chow group, and now you can compose. And so Chow motive, so over K, is just the following data: X, P, N, with X smooth projective, okay? P, a correspondence on X with which is an idempotent, so it should correspond to projection on some factor. And N is just here for the fun, it's number. It's important, but I want to explain. So now to X, you associate its Chow motive just, it's by definition the class of X. The identity, of course, is an idempotent correspondence. And you take for N to be 0. Okay? And then it's a theorem already mentioned by Gillet-Soulet, Gulen-Navarro. Now consequence of Bittner. There exists a unique such that you get the H of X if X is smooth projective. This works only in characteristic 0. In fact, to be honest, this is a corollary of results of these persons. So these corollaries can maybe be obtained as a consequence of Bittner, but they do much better. They construct, in fact, complexes of Chow motives, which is much better. And this result, which is much more interesting, is not a consequence of Bittner. So, okay. Now, remark. If one considers the motives, the Chow motive as a projective line, it's easily seen that it is it decomposes as follows. And hence, So it's also the image of the line, which we called L, is also called L here, and it is this guy. Okay. Now, yes.
Small title is not spec tail X, spec KX. The line is it spec K or spec KX?
No, it's spec K.
Yeah?
No, it's because, I mean, the number of points is 1 plus Q. So, I mean, the number here is just a way to express the state twist. So, okay, so that's more that I wanted. But now, if G acts, say, on smooth projective X, so you have a decomposition like this. Why? Just to alpha, you get associated a projector in the ring. QG. So I don't remember the formula, but it's something like that. And G induces the morphism. Say Fg from X to X, just multiplication by G. So you view it as a correspondence. So you have you have now you can define say capital P alpha to be this guy, the correspondence, and clearly it's a projector since this guy was a projector. So that's so simple, as simple as that. Okay. So and now so this construction so extends to G acting on any X at the level of virtual objects. And so this explains why to something like this, a Galois cover plus a central function. I don't remember the name of the function. Central function is a linear combination of characters. You may associate somebody in here, but you have to tensor with Q. In fact, the guy you want belongs to the image of K0 of variety tensor Q in this guy. And that's the guy we denote by that image by so finally, so we have say Of course, the main point is not explained here. Is why is it independent of choices? So the fact it's well defined, and this the proof you have to prove. It's not a trivial proof, and it uses in particular Chebotarev. So recapitulation. So if phi is say is a formula with coefficient in K, characteristic 0, you may associate to it an object here. But here you still have many invariants like odd numbers and Euler numbers. So a priori the Euler number is with values, take its value in Q, but in fact it takes its value in Z. So I'm very sorry for that. I mean, for a certain time, Jan and me were claiming everywhere that the values were in Q. But this is nonsense. I mean, in our paper we gave, in the introduction, an example which is dramatically false. And so, in fact, it should be really an integer because the number of points of sets in finite field defined by phi, they should be integers. Okay? When you count something, it's always an integer. So the Euler number should be also integral. But the Hodge numbers, they may be rational. So example, take K containing n roots of unity. So take the formula phi n saying that you are a power of an nth power, and x is different from 0, then the invariant of phi n is the following. So you have a rational number, but of course, when you take the Euler number, you get 0. And when you take the Hodge polynomial, you get uv minus 1. So Hodge numbers may be a rational number, and also they are not supposed. They may be not even positive.
Excuse me, that's an elementary question.
Yes.
Why does that image belong to image of the k-naught of varieties?
Can you repeat?
That image, you said image of those things coming from central functions on C, those
Not
covers. You said that image
No,
belongs to...
the one we are considering, I mean.
Yeah.
It's not true for any central function.
What was the central function? I forgot.
I mean, we were considering a certain kind of
these
special
counting
function.
functions,
Yes,
I see.
yes.
I see, that belongs to... Is that obvious?
More or less, yes.
And
No,
then
it's obvious because it's you use one uses the theorem of but Artin's theorem of induced character. So you express everything in terms of induced characters,
I see.
and then you reduce to quotients. And
Quotient curves and
Okay.
somehow can express it. And the thing was, after this, so you were saying that you used the earlier theorem that definable sets in pseudo-finite fields can be expressed in terms of these coverings, right?
Absolutely.
I see.
That's the whole point. Okay, so that's yes.
What happens if you replace y to the n with the general polynomial y?
Then it is what it is.
I mean, is the Euler characteristic always 0? Or
No, I mean, for instance, now if you don't put, if you replace, then you get a logarithmic 1. Okay.
So this statement you made earlier, independent of all those choices, is that fairly straightforward, or is that?
No, it's absolutely not straightforward.
Yes,
It's the heart of the. It's the way you have to work. I mean.
I see.
Now I have, I think, not a lot of time left. How much time do you have?
5 minutes. Maybe a bit longer because you started after.
I think I started after, no?
Yeah, yeah. 10 minutes.
Okay, 10 minutes is okay. 10 minutes is okay. Now we want to define certain series P sub R like arithmetic. And it will specialize to the p-adic ones. So the idea is simple, but there's a problem of language. I mean, so we want to express. So we are on ln of x. So for simplicity, assume x affine. So it's in some. Okay. So ln of x also is affine, and you have it's not obvious, but there exists a formula phi n, a first order formula, expressing that you have elements here that lead to arcs having the same residue field. So expressing that more precisely, when I apply this formula as a certain number of free variables, a lot of them, and when I look to the definable set defined by this formula over some field capital K, I obtain exactly that elements here that lived here. Okay? So it follows from path theorem that you have a formula. It's not obvious. Okay? So then you consider, you just define the arithmetic series. And you have the following theorem. So this series exists always if over fields of characteristic 0. So that's an advantage of pseudo-finite fields. I mean, if you have a certain field, you always have a lot of pseudo-finite fields containing this field, even if the field you're starting with is C, for instance. So if K is a number field, no. first, this series is always rational. And secondly, if K is a number field, you recover the Serre series. For almost all P. So you got what you wanted. So how do you prove such a thing? The rationality is proved. So I didn't mention how the rationality of the other one was proved, but it is just analog to the Deneff's proof of rationality of the Serre series. So you eliminate quantifier. You express the series as an integral, and you eliminate quantifiers, and you use Hironaka. So you do the same. And the fact that you have a relation with the number of points, it's because you mimicked in the pseudo-finite field setting what you do in the finite field setting to compute the number of points. Okay. And so this theorem may be, this part of the theorem may be viewed as a generalization of Axe-Cauchy type result. So I want to end by mentioning two things. So this is a special instance of a much more general result. You have a similar result holding for all p-adic integrals. So more generally, if you have a K number field, if you have you take L the path language, you take W, you take a formula F polynomial or a definable function. Then there exists a Motivic integral, say E mod, such that you get the corresponding p-adic integral. So which one? So you here you consider the set defined by phi in Kp n. So you assume it bounded. And here you integrate something like that. Okay. So the sets where you integrate, they are defined by formulas. That's the same formula for each p. F is a polynomial. It could be a more general function, but it would not add generality by a stupid argument. And there is a Motivic object, in fact, a Motivic integral, which specializes. So this is an illustration of a general principle. Natural p-adic integrals are Motivic. So of course this doesn't has no meaning, but and recently there were several papers by Hales. And he proved that orbital integrals occurring in p-adic representation theory and in Lagrange program are Motivic. Okay, that's almost all. I just want to mention something before the end. So in the first talk, I mentioned p-adic cell decomposition and a nice, beautiful result by Deneuve studying the variation of volumes or integrals with respect to parameters. And in fact, one can consider Motivic integrals with parameters and obtain a result of Deneuve type. And that's a part of work in progress by Ralph Kluckers and myself. Okay, I think that's all.
Any questions?
Actually, so Hales proved that any orbital integral is Motivic?
More or less, yes.
Yeah.
I mean, you give, you should really say which kind of integral,
Yes,
of orbital integral you consider, but he proved that, yes.
How does he come up with the motives that is, in some sense?
Oh, yes, the question is about
Sorry.
Hales' work. So Hales, using the general result I explained, is able to prove that all, between quotation marks, maybe, orbital integrals are Motivic. So he has to prove that everything you do when you compute orbital integrals can be expressed in past language and so on. This may appear quite straightforward if you don't think, I mean, at first sight, but it involves much more work than one could believe. I mean, it's not obvious.
I mean, but he seems to have nothing to do with usual ways of relating automorphic forms to motives or anything like this.
No, but Hales has a whole program, and it's maybe very long-term program, but the idea is that trace formula should be completely motivic. Should be an equality between two motifs.
But where the motives that appearing there have nothing to do with Shimura varieties or whatever?
No, but they are supposed to. I mean, the trace formula should tell you the motivic trace formula, which is still completely complete nonsense, is supposed to tell you that there is a relation. But I mean, Hales wrote a nice introductory paper to that program, and it's also a very instructive introductory paper to the work on Jan and myself. I mean, I learned a lot about what we did by reading the paper. Absolutely. The title of the paper is "Can p-adic integrals be computed?"
What about the classical as a basic functions and so on? What about
What about functional equations and so on? Are these of formal nature, motivic nature, or?
I mean, here for the p-adic integrals, it appears it's not always the case you have some functional equation. But in the cases where you have a functional equation over the p-adic, then we are able to prove the analogous functional equation of for corresponding Motivic integrals. And yesterday I mentioned the problem of the Astrovay zeta function. Then you have this mysterious Kapanov series. But in the case of curves, it's known, it's rational. And it's also proved that it satisfies the functional equation, the standard one.
But
And what is functional equation? Is of course, you have a duality, and you replace L by L inverse, of course. So you have in the duality. And I should say that the Motivic Kapanov series for curves, in the original paper by Kapanov, you have rationality and functional equation, but in a weak form. And in the second paper by Larsen and Lunds on the topic, you have a better statement, a stronger statement, and more geometric proof. So
because you say that function does not exist always. Can you give a
no,
easy example?
but speaking of two